lectures and 3 more hours of lectures two times. And so what I'm going to talk about today is I'm starting a new topic, which is the tree-based method. So there is a term related to this idea. It's CART, which is classification and regression tree. So that's the common name for the methodologies that I'm addressing today. Let me start sharing the screen. Yes, okay. So now I believe that I do share. So I apologize for uploading the slides late because I was busy with other stuff and I made last edits last night. So let's hope there are no typos left, although I believe there always is. Okay, but so I'm trying to catch them while I'm speaking. Okay, so here we go. So tree algorithms. So tree algorithms refers to a host of methods where you have a sort of systematically developing computational methods which are based on a very common practice, let's say in medical science, medical let's say medical practice, let's say. So when a person goes to a hospital or to a doctor, so typically what the doctors are doing, they are ruling out possibilities. And so this ruling out happens typically through a decision tree. So a sequence of questions are being asked, and depending on whether the answer is yes or no, you refine your diagnosis of what's going on. So therefore, since this practice is so common in let's say in field in medicine, for instance, and it's so heuristic and clear, these tree-based methods have gained certain popularity also in data science. The other thing that is nice, as opposed, for instance, to support vector machine algorithms, is that the tree-based methods give you a clear interpretation what your decision is based on. So you just follow the tree structure and you see what sequence of yes or no answers brought you into the conclusion that you have at the end. And so you can argue that following that tree, you see what are the decisive questions that sort of rule out certain possibilities. And in classification in particular, you at some point you start to see certain purity in the training set, and so then you see, okay, so this question was crucial, and that question sort of separated the current state from the competing possible explanation. So let me start with a simple idea here, which is exactly coming from the medical practice. So suppose a patient comes to an emergency room or to hospital, and so then what you want to do is to let me see, there are people waiting in the lobby, so okay. Just a moment, I'll check that there's not anything that I need to do. I believe it's okay. Okay, so I'll continue. So so a patient comes to an emergency room, and so let's say there are 4 questions that are being asked: the age, the blood pressure, fever, and white blood cell count. So this is just hypothetical example, and so based on the information that the patient gives, you have to give an assessment or how long this patient is going to stay at the hospital. So what we are doing here is so you want to create a function that, based on the answers of the patient, you give an estimate for how long the patient is going to stay in the hospital. Okay, so the attributes are the age of the patient, blood pressure, fever, and white blood cell count. Okay, so so this is a hypothetical example. And so what you want to do is, of course, you want to base this decision protocol on earlier data. So you have seen patients coming in, giving answers to those questions, and you know more or less how long they stayed at the hospital. So now your tree algorithm should be such that when the answers are given, the answers give you a rough ballpark estimate of how long the patient is going to stay in the hospital. So what we start is with the training set. So this is the training set in this case would consist of data vectors, which are exactly the answers of P patients to those questions. Okay, so we have patient one, patient. Oh, there are some rumors that I don't know where they come from. Okay, so patient one gave you answer to those 4 questions, and then you later observe the stay length at the hospital, and that's Y1. So Y1 is the length of the stay of patient 1 in hospital. Y2 is the length of the stay of patient 2 in the hospital, etc. And so now your mapping F would be such that more or less this F, when you give the answers of the patient XJ, you get as an output the length of the stay in the hospital. So the decision tree means that you ask like simple yes/no questions. So you, for instance, decide that 38 degrees of fever is considered to be high fever, low fever. So okay, so now you ask if the patient has fever over 38 degrees, yes or no. So the third attribute is the fever, and so you check if X3 is larger than 38, and if the answer is yes, you say, okay, so the stay at least 2 days, so that could be a possibility. Then you look at the blood cell count, and so you are interested in the neutrophils, and so you say if the neutrophil count is less than 1,500, which is considered to be a low count, so then if that's lower than the low counts, and then the stay at least 2 weeks, etc. So you are sort of deciding what the critical value is, where you decide if you go up or down, or no, if you consider that the answer to be yes or no. So you want the solutions to be binary to each question, and so based on this binary question outcome, you decide in which category you classify the patient. So that's the basic idea of a tree. So here's a picture. So here I have 2 possible questions. So I have attribute S1 and I have attribute S3. And sorry, I have attribute X1 and then I have attribute X2. And so I have let me see, there is something strange in this picture. This is not the picture that I wanted to show you, but maybe this explains anyway. So okay, yeah, well, it is actually, yeah, that's fine. Yeah, so let's think that you have a 2 attribute data set. Okay, so there are X1 and X2. So your first question is X1 larger or equal to S1 or smaller to S1? Or actually here I'm asking is X1 is smaller than X1. So if the answer is yes, so look at this picture here. So then you split the field in 2 along this line where X1 equals S1. So if the answer is yes, you place your patient to the left field of this rectangle. If the answer is no, you place your patient to the right field of the angle. Now suppose that you are placing the patient to the left field of the angle. So your X1 was less than S1. So we are in the domain where X1 is less than S1. So then you are asking a question, is the value X2 larger or smaller than S1? So S1 is this value here. Okay, so then if the answer is yes, so then you say that the patient gets value C1 from his input data. So the input data of the patient leads to conclusion C1. Whereas if the answer to the second question is no, then you decide that the answer is C2. Similarly, if the patient answered no to the first question, now you ask another question and you are using another value for x2, asking if x2 is smaller than S3. If it is, then you give value C3 for the patient, and otherwise you give the value C4. So what you can think here is that you have a function of two variables, x1 and x2. And you are approximating the function by a piecewise constant function. And you are representing this piecewise constant function as a tree. So tree represents actually a function here. And so the graph of the function in this case, this is a very simple tree, is this rectangle here where the values C1, C2, C3, and C4 are coded here as colors. And so you can think that this is sort of an image which represents a function. So it's a function which is approximated by piecewise constant in this way can be identified with a decision tree. And so this is the idea of regression tree. So if you have a function which is defined as a function of x1 and x2, you are doing regression. So you are approximating your function with a piecewise constant function. So at the end of this set of lectures, I'm going to show how you use these regression trees to approximate, let's say, images, for instance. The other thing that we are going to discuss, and that's the first topic that I'm addressing, is the classification. So this is a regression tree, and now we're looking at the classification tree. Okay, so we have sort of two tasks: approximating a function by a tree, or making decision based on a tree. So they are two similar but different tasks. So here is the classification problem. So suppose you have k classes in which you can classify your cases. So you can think that you are asking, for instance, does the person has pneumonia or not? And so you have, so then you have two classes, pneumonia and something else. And so you want to classify the patients in one of those two categories. And so then you have a sequence of questions. And when you ask those questions, you end up saying, yes, I believe that this person has pneumonia. So the classification is 1. Or you say, well, it seems that this is not pneumonia, so it is class 2. So we have k possible classes here. So CP is the class of the training data. So this is always, we train the system with the training data, and then we use it for classification later on. And so we have these P training data sets which have been classified by an expert. So we know what class these cases belong to. And so then we are trying to build the classification tree based on that training set. So again, we do the same idea as we did in the regression. So the basic idea is that we divide the data space in rectangles. So if you have two attributes, let's say fever and age, so you are in two-dimensional space, and so you are dividing your two-dimensional space in rectangles. And each rectangle represents one class. So now if you have a data point X, which you don't know what the classification should be, you check in which rectangle X belongs to. And then you classify this X using the majority vote typically of the data set in that rectangle. So suppose, let's go back here. So suppose that in the classification case, you have these rectangles here, the C1, C2, C3, C4. And so then I give you a vector X and you end up, let's say, in the rectangle C2. So then you go and see what the majority of the cases in your training set in this C2 represent. And then you classify to that class according to the majority vote. And so if all points in the training set are in one class only when you end up in this rectangle C2, then it's very simple. You say, well, this rectangle represents as let's say case 1, and so therefore since my x ended up in that rectangle, I'm classifying my x to class 1. So now the question, of course, is how we choose these rectangles and how do we decide in which rectangle x belongs to. And so this is exactly the tree algorithm that is answering to both questions 1 and question 2. So I hope this setting is clear to you. And so here is another picture. So this is the classification idea. So I have a rectangle. So in this schematic toy example, I think that I have two attributes, x1 and x2. And then I have, since this is training set, I have a classification of my data in class 1 or class 2. Class 1 is denoted by these green rectangles, and class 2 is denoted by red dots. So this is my data, which is placed into this x1, x2 space according to what values the attributes take on in the training data. And so in the tree algorithm, what we do is we try to divide these rectangles into smaller rectangles that do a better classification than just saying that it is either 1 or 2. So here is, if you go counterclockwise, so 1, 2, 3, 4. So you see what is happening here. So first I'm splitting my rectangle with a horizontal line. So in this case, my first question would be, are you below or above this value x2? And so depending on the answer, you end up into the rectangle up or in the rectangle down. So that's my first classification. Obviously, if you look what the division line creates, it doesn't really give you much of a hint which class you should classify the patient into or the case into. So therefore, you need further division. So let's look at the upper rectangle here, where you have 3 green squares and you have 3 red dots. So if you divide that rectangle with a vertical line, as in this box number 3, now you have boxes which contain only cases belonging to one and only one class. Okay, so if you answered my first question that you are above this horizontal line, and you answer to the second question that you are on the left or right of this vertical line, then I have a classification for you. So you are either in this upper box, and I'm classifying you to the green class, or if you are to the right, I'm classifying to the red class. And then finally, since some people are not above this line, they are below. So therefore, I'm dividing also the lower rectangle into 2. And so now I have 4 rectangles, and each one of them represents one and only one class. And so if you answer 2 questions, you end up in one of those boxes. So 2 yes or no answers will lead you in one of these 4 boxes, and then the classification follows because you classify to the class where obviously the majority is defining what the class is. And so in this case, majority is a pure majority, so there is no ambiguity. So often people are talking about majority vote here, so you can think that these training set cases are voting. So these votes are unanimous. So unanimous. So they unequivocally are classified to one of those classes. Now naturally, we have to remember that when you collect data, including the training data, the data is always noisy. Noisy means that the value of the attribute is not perfect. And so you can think that, let's say, for instance, this red dot, when we collected the data, it contained so much error that actually this red dot would belong to this upper left rectangle. And so you should not expect perfect classification ever when you use these trees. But so we'll address that question later. So the noise in the data will make this algorithm such that you don't always get pure classes as we had here. And sometimes pure classes may be misleading because they are sort of relying too much on the training data. So sometimes you have to relax a little bit of the, the classification purity to take into account the fact that the data is always noisy. Okay, but so this is the idea. So now the question is, how do we do the splitting? So here I just draw these lines, and it was easy for me because I had the two-dimensional data, and so I'm just looking at the data, and so it's easy for me to do this drawing. So when you have 700-dimensional data, you cannot look at the data like this. You can always try to do the PCA, reduce the dimensionality, but if you do PCA, you lose the nice structure of the yes/no type of navigation in the data space, because when you reduce the data, you no longer you see that the principal components are linear combinations of the attributes, and so you don't have any longer a yes/no question. So you cannot ask, do you have 0.6 times fever larger than something plus 0.4 times age larger than 50, so that doesn't work. So we need to have the questions related to the original attributes. And so you really need to be in this high dimensional space. So dimension reduction in this tree-based method is not working. And so therefore, we are in an abstract high dimensional space, and we need to have an algorithm that doesn't rely on our looking at the data so that we can do the classification. Okay, so therefore we need to define something which is related to the purity of the rectangle. So if I have a rectangle, so here, so let's look at the first rectangle. So this first rectangle is not pure because there are lots of both types of data points. Whereas if you look at this rectangle here in case 4, all these rectangles are pure in the sense that there's only one type of data in each rectangle. And so in order to quantify this, we need to define a concept of purity. And so let's see how we do that. So we start with some basic concepts here. So R in my presentation now refers to a rectangle where sides are parallel to the coordinate axes. So exactly, you can think of this two-dimensional rectangle, but of course we are in higher dimensional space. So in 3D it would be a rectangular sort of parallelepiped or rectangle, what we usually mean by a rectangular object in 3D. In Rn, it's something which is just a definition of Cartesian products of intervals. So sometimes these rectangles are called intervals because one-dimensional interval generalized to higher dimensions is just the Cartesian product of one-dimensional intervals. Okay, so now we have a training data t, so x1 is to xp, and so we assume that this is annotated, so we know exactly in which class each one of these data points belong to. And so I'm going to denote by cj those classes. And so what I'm defining now is, let's denote by nr, the number of data points in R. So the total number of data points. So if you are in R, if all these x's are in this rectangle R, so we are not looking at the full rectangle, not the sub-rectangle, so this nr would be p. If this R is a smaller set of the original data space, so then my nr is smaller than p. But so this is the number of points that I have in my rectangle R. And so then I need to measure how many of those points belong to different classes. So if I'm denoting by nj R, the number of data points in R that belong to the class J. So I'm looking at the annotation and I'm deciding in which class they belong to, and then I'm just counting how many I have in that class. And so now you see that the total number of points is simply the sum of the number of points in each class, because the classification is unambiguous. So we know exactly in which class the training data belongs to. So nj's add up to Rn. So this is my first observation. And so therefore, if I divide this equation here by nr, So I get 1 equals sum nj divided by n. So that's what I'm doing here. So you get this PJR, which I refer to as frequency of class J. Sometimes people are referring to these as probabilities, and so of course this is the frequencies concept of probability. So the idea is that if I randomly pick one point from the rectangle, what is the probability that that point belongs to the class J? And so the probability in this frequentist tradition is of course the same as the frequency. The probability is the same as the frequency. So nj divided by n. So if you have 1/2 and 1/2 in two classes, so then these PJs are both 1/2. And so the probabilities of frequencies sum up to 1 because we got this ratio, this equation by dividing this equation by n. Okay, so I use I believe that in my notes I'm using the word frequency, but if you prefer probability, that's fine too. So sometimes it's easier to think of in terms of probabilities rather than frequencies. So in this case, they are synonyms here, and so you can form a vector P, and this P has components Pj, and so of course you can now draw a histogram of this vector. And so that histogram is telling you how the points are distributed. So here is an example. So I have a rectangle and I have 3 classes. And so I'm counting how many red points I have, and how many blue points I have, and how many black points I have. I normalize those numbers by the total number. And so I get this histogram. And so you see that the red class is a dominant class. So the largest probability when you are drawing randomly from this box a point is that your point is going to be a red one. And so red represents here the simple majority, not well, it is the most abundant vote, let's say. So if you need to vote. So if you use this rectangle to classification, and you would say, okay, so which class is my unknown belonging to? Your best bet would be that the point is belonging to the red class, because that's representing the largest class in this rectangle. So these histograms are sort of representing the probability distribution, if you wish. Okay, so here is the principle of majority vote, which I already indicated. So if you are given a new data vector x, and that x after a process, you find that it is in a rectangle R. So then if you want to classify this x using majority vote, you choose the class according to who is the dominant class here. So in the previous case, red would be the class attributes that I give to x. So we have this winner takes all approach. So you could use also some sort of fuzzy classification, saying that the probability of being in this class or that class is according to the frequencies of the different classes. Here we just simply take this winner takes all approach, and we are saying that we are classifying into the class of the largest representation. Now, if you have a tie, so if you have, let's say, 50-50 situation or 1/3, 1/3, 1/3 situation, so then you can think that the classification can be done by flipping a coin. So we choose randomly among the winning classes. So if you have several winning classes, we leave it to the random process of flipping coin to decide in which class you are classifying your point x. This is again something that you can criticize, you can modify, but at this point we are assuming simply that we are doing this way. Okay, so majority vote principle is the one that we are using. Okay, so then when you do the classification, you can ask what is the misclassification error, and this misclassification error is the relative amount of elements that do not represent the majority. So you decide which the majority class is. And so then you sum the frequencies of those points which are not belonging to the majority class. And the other way of saying is that this misclassification error is 1 minus the frequency of the winning class. So for instance, in this case, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. And so if you ask, so red is the dominant class, so you can argue that the misclassification error in this rectangle would be 0.5 because 1/2 of the points do not represent the majority class, which is the red one. So here the misclassification error would be 0.5, which is rather high, I would say. So 1/2 is misclassified. So we have this misclassification error. There are other measures of impurity, and so here are the one that we are going to use, which is called the Gini index, and the Gini index is the sum of the products of Pj minus 1 minus Pj. So it's not immediately obvious why this G here is representing the impurity, but so let me try to explain. So first of all, this Gini index can be written in different ways. So if I distribute this product here, Pj times 1 is Pj, so this is the first term, and then Pj minus Pj squared. So what I get is the sum of Pj's minus the sum of Pj squared. And so now remember that the frequencies, they sum up to 1. So Gini index can be written as 1 minus the square sum of all these frequencies squared, square sum of the frequencies. Okay, so how does this measure impurity or purity? So let's see. Suppose you have all the entries in one and only one class. So then these Pj's are all zeros except for one class, and so then you see that the Gini index will give you 0, because if you are in one class only, so then either Pj is 0 if you are in the non-winning class, or 1 minus P is 0, P is 0 when you're in the winning class. So you see that this Gini index is somehow so it is vanishing if you have a pure class. And if you have, let's say, two classes and you have the 50-50 situation, so then Pj is 1/2 and 1 minus Pj is 1/2. So Gini index takes on the value of 1/4. And actually this 1/4 is the largest value that the Gini index in a two class situation can have. So the Gini index is something between 0 and 1/4 in that case. And so the closer you are to 1/4, the closer you are to the case where you are indecisive. And the closer to 0 you are, the closer you are to the pure class case. So this is really an impurity measure. So the larger Gini index is the more impurity there is in the class. So there's another concept which is called the cross entropy or entropy. So maybe this cross entropy could be taken away. So entropy, and so those of you who are familiar with the Shannon entropy or entropy in general in statistical physics, this looks very familiar. So if you have a probability distribution Pj, so then the entropy of that probability distribution is minus P log P and then sum over the classes. So again, the entropy is largest when you have impurity, and the entropy is lowest when and it's 0 when you are in a pure class. So we interpret that 0 log 0 is defined as 0. So because if you don't have one class here, then you have to decide what you do with 0 case. And so we are deciding that P log P when P is 0 is defined as 0. And so this entropy is largest for a mixed class. So we are not using this entropy, but I wanted to show you because some people like to reason in terms of entropy. What I'm using here is the misclassification error and the Gini index. So those are the two quantities that we are using in our construction. So here is my example that I already indicated. So suppose you have a data points from two classes in a rectangular one, and you have 5 data points. And so if they are in one single class, say in J1, so then the frequency of the class 1 is 1, the frequency of class 2 is 0. So I have a 1, 0 case. And so now the impurity index, let me see, so misclassification error, this one here. So the misclassification error is 1 minus the frequency of the winning class. The winning class has frequency 1, so you get 0. Gini index is 0 times 1 minus 0 plus 1 minus 1 minus 1, and this is 0 as I explained. And the entropy is minus 1 log 1, which is 0, and then 0 log 0, which we interpret to be 0. So all these quantities give you, in this case, that the impurity is 0. Whereas if we go to the case where we have 3 data points from class 1 and 3 from 2, so in this case we have 2. We have a rectangle R2 which has 6 points. And so since we have a draw situation, we are not able to use the majority vote classification, so we flip a coin. And so suppose that the class 1 wins when we are flipping the coin. So the frequencies are both 1/2, and so. And I said wrongly. I said the Gini index is 1/4. It's 1/2 in this case. So let's see. So the misclassification error is 1/2. So 1/2 of the points are classified incorrectly. And Gini index is 1/2 times 1 minus 1/2. So it's 1/4. That's what I meant. But then of course there is the sum over all classes. So I have 1/2 times 1 minus 1/2, which is 1/4 plus 1/4. I get 1/2. So both for misclassification error and Gini index, the maximum value is 1/2, and for the entropy, this is logarithm of 2. So this is the maximum number. Anyway, so you can define many other impurity indices if you wish, but these are the most commonly used. And so as I said, I'm not going to use this entropy measure, but you may see it in some tree-based methods, algorithms, and so therefore it's good to know. So good. Okay, so now what we are going to do, we are looking what happens if you split a rectangle in two. So you are having a rectangle which contains training set, and you have a certain impurity of the data in your rectangle. Question is, what happens if I split my rectangle in two? And so in particular, what happens to the overall impurity in this situation? So given a rectangle R in Rn, which has sides parallel to the coordinate axis, we are splitting this R in two at a value S. So first of all, what we do when you do splitting, you need to choose the attribute according to which you are doing the splitting. So you choose one of those attributes from 1 to n, and then you're asking whether this attribute number j is larger or smaller than s, which is a value that you decide at this point. And how we choose this s and how we choose this j is exactly what this tree training is about. So at this point, we are just looking at, suppose you have j and suppose you have s, what happens? Okay, so we are splitting corresponding to JS. So the splitting is given in pairs. So we give the J the coordinate or attribute that you are using for splitting, and S is the value. And so then I'm splitting R in two pieces, RL union RL, and so these are R. So these are left and right. And what I'm assuming here is that my data is finite. So I can always choose the splitting S in such a way that each point belongs exactly to one of the rectangles. So technically, I could say, well, if I'm splitting this way, if you have the data points on the boundary, then it goes to the right rectangle. And so choosing the boundary to belong to the right rectangle is rather arbitrary. So we don't want that sort of arbitrariness. So usually when we do the splitting in practice, we are choosing the splitting values in such a way that it just neatly goes between the data points, so that the data points are neatly on the left or on the right, but not right on the boundary. But for the sake of generality, I'm assuming here that the boundary values are sort of attributed to the right rectangle, so that's not that important. So we have two disjoint rectangles that we are dividing our original rectangle into. And so let's see what happens to the purities. So G is, remember, this is the Gini index, and so I can calculate the Gini index for the original rectangle, and I can calculate the Gini index for the left rectangle and the right rectangle. And so those values are GR, GRL, and GRR. So I have these three impurity measures for those three rectangles. Now I'm defining my delta G as the impurity change, and this impurity change means that if GR is the original impurity of the whole rectangle, so I'm weighing this impurity of the left rectangle by the frequency of points that went to the left, and I'm weighing this GRR with the frequency of the points that went to the right. So if you think in terms of probabilities, what we are looking at here is that, so you can classify your point using the original rectangle, or you can use the classification using the right or the left rectangle. And somehow this delta G is telling how much better you are doing the classification when you are using the finer rectangles. But we don't need to interpret, because this G is not really a probability here. So I'm simply saying that the impurity is, let's say, it is decreasing. This is, now I have to be careful. So impurity is increasing if this dg gets smaller, right? So we want this delta G to get smaller, so that the impurity is decreasing when we are splitting my rectangle. So it would be nice to see that this dg is negative, right? So impurity is decreasing, yes. So we are looking at the change, the overall change in the impurity. So notice that the ratio NRR over NRL divided by NR, that can be interpreted as the probability of the data points to fall to the left or the right of the split. So if you want to use this probabilistic sort of interpretation, so then this is the probability that you fall to the right or to the left. And the important thing, of course, is that the number of points on the left plus the number of points on the right, that this equals the original number of points. So we don't lose any points here. So they are either on the left or to the right of the split line. Okay, so my question is, how does this delta G behave? So am I doing better in terms of impurity if I'm splitting the rectangle, or am I doing worse? And this following theorem says that delta G is positive. So let me see if I did the wrong interpretation. So delta G is positive. So okay, yes, I said that I want to be this negative. Of course, I want to be positive, because this is telling me how much the impurity is decreasing. Sorry, yes, I knew that I wasn't reasoning right in my words. So this delta G is telling me how much the impurity is decreasing, right? So we start with this original impurity, and then we are seeing how much it's decreasing. And so what we want to see is that, of course, the impurity is decreasing. So that therefore this delta G, which measures the decrease in the impurity, that should be positive. So we need to have a decrease. And this theorem here says that indeed, when you do this splitting, no matter where you split, you cannot have a worse situation. So the impurity is decreasing. Okay, so this is the first principle here. So it is always advantageous to split a rectangle in terms of the impurity. So you will always have more less impurity in the new case. So that's my first theorem. So let's see how we are proving this. So first of all, I am defining this new L and new R as the frequency or the probability that the point falls to the left or to the right. And so the sum of those two frequencies equals 1. Okay, so this is the first observation. So remember, eta is the frequency of being on the left, being on the right. Now, GR by definition. So there were two. There was the original definition GR, and then I told you that this GR can be also written as 1 minus the square sum of the frequencies of different classes. So this is my G, and likewise I am writing the Gini index for the left and the right rectangle. So 1 minus the frequencies of each point belonging to the class J in this rectangle RL or RR. And so now when we are writing this delta G using this notation, frequency L, frequency R, this change in the Gini index is the original Gini index minus the frequency times the Gini index on the left minus the frequency times the Gini index on the right. And so let me see, I can write this here in a different way. So I'm plugging in this GR and GRL and GRR from the previous line. So I'm just substituting these values into my expression. And you see that these ones cancel because this one here is multiplied either by new L or new R. And since the sum is 1, they cancel the 1 in this Gini index GR. And so what I'm left with is the sum of the frequencies of new L times the Gini indices, sorry, the frequencies on the left squared plus the frequency R times the frequencies on the right minus the frequencies in the original rectangle, all squared, of course. And so this is just an identity that follows simply by substituting these two quantities into there. So this is my expression here. Now I want to show that this number here is positive. So what I'm doing, I'm rewriting this PJR. So PJR, which is the frequency of a point in the original rectangle being in the class J. So I'm writing it in terms of the frequencies being on the left or being on the right. And this is some sort of if you want to use the terminology of probability, this is the formula for total probability. But let's see how I get it. So the probability or frequency of being in the class J is by definition the number of points in class J divided by the total number of points, and then I'm dividing this number of points being on the left or the right. So being in the class to those which are on the left and to those which are on the right. Okay, so this is an identity. And so then I'm dividing both of these terms separately by NR, and I'm dividing and multiplying by the number of points in the left rectangle. And likewise, I'm doing the same thing with the right rectangle. And so when you're looking at this expression here, so you see that here I have the frequency of being on the left, and here I have the frequency of being on the right. And so here I have the frequency of being in the class J, given that you're on the left, and here is the frequency of being on the right, given that you are in the left in the right rectangle. So you can interpret this PJRL and PJRR as conditional probabilities, Okay, so it is the probability of being in the class J given that you are in the left or given that you are on the right, times the probability that you are in the left or you are in the right. So you see that this is really nothing else but the formula of total probability. But so you don't need any probability calculus to understand this. This is a straightforward argument, as you can see. So now this is nice because now I can write this PJR in terms of the PJs on the left and on the right. And so I go to this formula and I replace this PJR with this formula. So my delta G takes on this form here. And so then I'm distributing this binomial term here. So I'm distributing this binomial formula. I'm using the binomial formula, and so I'm collecting the terms which are proportional to the frequency Pj on the left squared. So I get nu L minus nu L squared from here. The same thing with the right parts are nu R minus nu R squared, then minus 2 times nu L nu R, and then the product of these frequencies. And so now I'm using the fact that I'm looking at this quantity nu L minus nu L squared. So I can take nu L as a common factor from here. So if I take nu L minus nu L squared, taking nu L as a common factor, I get nu L times 1 minus nu L. But so remember, these frequencies sum up to 1. So 1 minus nu L is nu R. So this nu L minus nu L squared is simply the frequency nu L times nu R. And the same is true for the right frequencies. And so therefore my formula on the previous page, so you can replace this expression here in parentheses by this nu L nu R product. And same thing here. And so therefore all these three terms have a common factor nu L nu R, which I can take as a common factor and pull out from the summation. And so what I'm left with is a sum over the classes of Pj in the left squared plus Pj on the right squared minus the double product of those. And so of course this is a binomial formula, and so therefore I can collect these terms to be Pj minus Pj on the left minus Pj on the right squared. And so you see that this is positive. And so this completes the proof. So now we can actually see when the Gini index does not change. So when delta G is actually 0, it is exactly when you go and split your rectangle in such a way that the proportion of points in different classes on the left and the right remains unchanged, so that Pj on the right and Pj on the left is the same. So that means that if you had originally 4 points in class 1 and 4 points in class 2, so when you do the splitting, you have done the splitting in such a way that you have 2 points on the left and 2 points on the right in one class, and 2 points and 2 points in the right. And so then these Pj's are equal and this delta G vanishes. But so we are trying to make this delta G as large as possible, so that when we choose the splitting, we are improving the purity and decreasing the impurity. So that's the idea. So what the conclusion of this proof is that each split, no matter how you do it, improves or at least does not deteriorate the purity. So you cannot do worse if you split. But obviously, if you choose your split in a way which is not changing the ratios of the classes, then you are not improving either. So you are adding to the complexity, but you are not improving the purity, which is something that we try to avoid here. Okay, so the more you split, the more complex your situation is, of course, the more splits you have in your tree at the end. And so we're trying to do it in an economic way. But the important thing is that you can't go astray if you split. So now we start defining a little bit more graph theoretic structure here. So the tree is a graph. And so we need to introduce a couple of terms from that sort of graphs. And so the first thing is that if you look at the tree, we call a rectangle a leaf if it has no offsprings. And so what is an offspring? Offspring is a subrectangle. So let me go back. I'm showing this in this graph picture here. So here is a graph, and so these yes or no questions. They correspond to rectangles in your data space. And so when you come to here into the last row, the lowest row in my tree, you see that these C1, C2, C3, and C4, they correspond to these rectangles which have a different color, and so they don't have offspring. So I can argue that this box here has two offsprings. And what does it mean? It means that the rectangle on the left has been split into other rectangles. So I'm saying that the rectangles, so I'm referring to the rectangles as if they were members of this tree, in the sense that the rectangle, which is consisting of C1 and C2, it is not a leaf because it had two offsprings, C1 and C2. Now, C1 and C2 are not split, and so therefore I call them leaves of the tree. So the entries here on the lowest level where you don't go any further, so there are no more splittings. These rectangles are going to be called the leaves of the tree. So that's my language here. Let me see. We were here. So yes, a rectangle is a leaf if it's no longer split. So that's my definition of leaf. And so then I'm also defining a pure leaf. A pure leaf is I mean a leaf that has the Gini index equal to 0. So again, let's go back here. In this case 3, when I have not split all the way to the case 4, I have two pure leaves. I have the leaf containing these 3 green rectangles and another pure leaf up here. If I don't split the last rectangle any longer, this lower rectangle is a leaf because there is no splitting, but it's not a pure leaf because I have 2 mixed classes. Whereas if you go to this 4th split case, you see that we have 4 leaves, and those 4 leaves are all pure. So pure leaf means that there is only one type of points in that rectangle. So this is my definition for a pure leaf. And so if the leaf is not pure, then it's called mixed. So I'm going to use this notation R, script R, P for the collection of leaves which are pure, and then the collection of leaves that are not pure is Rm. And so today we are only having 1 hour time, so I'm not going further here. I'm just explaining you a little bit how this story goes. So what we are doing, we are taking leaves from the mixed set of leaves, and so then we are splitting the leaf. Now, when you split the leaf, it's no longer a leaf, but it produces 2 leaves. And so then you take those 2 leaves and you check if they are pure or not. And so if they are pure leaves, you put them into the RP. If one of them is pure and the other one is not, you put the pure leaf in the RP and the mixed leaf back into this set of mixed leaves. Or if they are both mixed, you just put them into this RM. So the process is as follows: you take 1 leaf at a time from the set of mixed leaves, and then you split, and then you check if the new leaves are pure or not, and then you place these new leaves in one of those sets. And so this is the process that we are going to follow. And so the criterion how we choose the leaf is we try to choose the leaf in such a way that we have the best possible increase in purity, so that we make the most economic tree possible, so that every time you split, you increase the purity as much as possible, so that at the end you have just pure leaves. And so that's the so-called maximal tree that we are going to construct. So I will stop today here. And so next Tuesday we have 2 hours, and then Thursday we have 1 more hour. And I am not sure if I will have enough material of this tree section for all 3 hours. If I don't, then I'm going to add 1 more topic to the list of topics of this class. If I go, let's say, slow enough, so to speak, we will finish next week the details of this tree-based method algorithms. And so we are going to look at a cool application also, which is image approximation by regression trees, which is really fun. Okay, so thanks for joining today, and next week we will continue on Tuesday from here. And also I have promised to select the problems that you need to do in order to let's say pass this class, and so I'll try to do this over the weekend so that you can start working on the assignments. Okay, so thanks everybody, and see you next Tuesday then.
Bye.
Thank you. See you.
See you. Thanks.
Thank you, Professor. Bye. Bye.
Ciao, ciao, Erkki.
Ciao. Ciao.